so we are doing lecture 11. And what we've done is memory elements, then we said latches, then we turned that into a D-latch, and then we tried to build a counter. It didn't work because of transparency issue. We resolved that by complementary D-latches, and then we came up with the flip-flop. That's what we have now. What is a flip-flop? Well, and then something else that we did, we turned the entire circuit into NAND. And so we said that each latch really looks like this. This is the D input, and this clock Q, and always Q bar. Okay, so this is a D latch. And yeah, something else we did, we first started with the D flip-flop, and then we went back and fixed the SR and came up with JK, and then T flip-flops as well. Okay, so this is the D latch, and what we will be working on for most of the time will be a D-latch like what I'm showing above. Okay, and so this is C1 1D. That's a D input, and then I have, let's say, C2 2D, just to separate them. And this is complementary, and the output from one, which is the Q output, goes into the D input of the other one. And this is actually my flip-flop. Okay, two complementary D flip-flops, and we call this one master slave D flip-flop. And this doesn't have the transparency problem. Inside each one of this is one of this. Okay, something like this. All right, so that's where we are now. And then we did something here also. We said this master slave D flip-flop, the symbol for it can be like this. Okay, notice that in addition to the C1 that I have for the clock, I also have a kind of edge, something like this, next to C, indicating that my output changes with the edge of the signal on that particular input. Okay, and that's the symbol, but that's exactly where the problem is, which I'm going to talk about today and make some corrections. What it is if this is the C input, we talked about this before, and the D input is taken the D input is taken here, Okay, it takes some time, and then going back again to this, the D input is taken by this when clock becomes 1. Okay, goes through, sits here, and sits there, does nothing until my clock goes back to 0. When it goes back to 0, then the other one becomes operational. This one becomes operational, and I see my output after the clock has already made a transition. And that's exactly why we are using this symbol, which I erased, this symbol, and this is what we are talking about. Okay, the symbol next to clock is indicating that I actually have my output affected when this one goes to 0. All right, so that works. What's the problem? The problem is that I have some delay the orange area and some delay the blue area that they add together and put a limit on how fast my circuit can become. And that's the problem we are solving today. And before doing that, I like to do the very long descriptions of them also, of whatever we have so far. One is the D-latch, and the D-latch goes like always at C or D, and then I say if C means if C is 1, Q gets D. And for sequential circuits and for memory circuits, for constructs that do have some memory, instead of using this, which I used in the descriptions you have seen before, I use this. This is called a blocking assignment. This is called a non-blocking assignment. Okay, I'm not going to explain why we use non-blocking for sequential circuits, but as a style of description, use what I'm telling you, which is the non-blocking for the sequential circuit. So this is the description for the Q. Now, whether you want to put it inside a module or as part of a bigger module, doesn't matter. In any case, though, the Q output has to be declared as reg because it is being used on the left-hand side inside a an always a statement. Okay, and so how about the D flip-flop? A D flip-flop again has a Q output. In addition, it has an M output, that is the intermediate output, and I'm gonna write exactly this, where this middle point is M, and then I also have a clock and a clock bar, CB I'm calling it, and therefore so this is D flip-flop, or let's call it master slave, D flip-flop, and then I have a wire, CB. Okay, and I show you this construct that we use in Verilog. I can combine an assign statement and the declaration. So instead of saying wire CB and then say assign CB equal to clock bar, I can just say assign CB equal to tilde clock or clock bar. Okay, and so my CB is known with that inverter inside, and then I have a Q and M, and then I say always. Let's do the left one first. The left one, the input of it is D and C, and then I say that M gets D, but see, M is not the final output. Then I have another one. I'm sorry, I missed the if C, M gets D, the next one always at, then the input of the next one is M, the clock of the next one is CB, clock bar, and then I say if clock bar, then Q gets M. All right, so I did exactly what this structure is showing, and one of them is the left hand side, one of them is the right hand side, and okay, this is the right hand side one, and then this one is the left hand side one. Okay, so this together is the master slave D flip-flop, but then there are other better ways of describing it, which I will do later on. And so we are done with basically explaining all of this, and let's see if there is anything else to be said, and for now we are fine, and let's go into what I was talking about, and that is the problem with this delay. Okay, if you look at the structure I was showing, the problem with the delay is very clear. Okay, on the orange side, D has to propagate through the left latch. Okay, right? On the positive side of the clock, it has to propagate through the left latch, which means that it does need some propagation delay. Okay, I will not be able to pick up M until that propagation is complete. That means I have to allow it some time. But then, once that is there, then when the clock goes the opposite, that means the clock becomes 0 now, then that again has to propagate through the blue, and therefore there is that delay there. Okay, these two delays add, and then this puts the some clock frequency maximum limitations. Okay, or the minimum for the clock period. To resolve this issue, look at each of these structures here. Okay, I've shown the gate level structure right above the orange latch, and you're seeing that there is a two-level logic, one for the clocking. Okay, so there is this logic level, see, there is this logic level, and then there is this logic level. Okay, which means that for the clock to affect the Q output, it has to go through two logic levels. The question is if I can reduce that, and there are two levels here, then there's another two level for the blue part. Okay, and I'm not going to tell you exactly how this flip-flop circuit is reached, but I will do the analysis. I tell you how it works, but not how it was developed, how it was designed. So I still have that NAND structure, that cross-coupled NAND. On the output, I also have a cross-coupled NAND. Okay. This is my D. This is my clock input. This is my clock input. Like I said, I'm not going to explain why, how this circuit is reached, but you will see that it really works, and it works very nicely. And then I have a crossing from here back to this. And I have a crossing. Oh, this is a challenging one. Okay, back to this, and this is good for now. Let's analyze it. Okay, let's do what we did before, and I'm starting with C 0, D 0, and Q 0 for now. Okay, and initially C is 0, D is 0, Q is 0. Then I will analyze it to make sure that the circuit is stable. So with these values here, C is 0, therefore a 0 on the input of a NAND gate, the output is 1. Okay, so this is a stable value 1. D is 0, so there is a 1 here as well. C is 0, therefore this is 1. Okay, and Q is 0, and therefore this is 1. Now look at the output. I have a 1 on the upper gates inputs, okay, 2 1s, and therefore yes, indeed the output is 0 and it's held at that value. Then I have a 1 coming into the AND gate and the lower AND gate, this one, and the output is 1 indeed, and so the only gate that I don't have the output yet is that very upper gate there. And then look at that, it has a 1 here. Okay, it has a 1 on the upper input of it, it has a 1 on the lower input of it, and therefore this is 0. Okay, that's the stable situation. Now I'm going to play the same thing I did before. So what I'm going to do is I'm going to change an input. Once I change the input, I will propagate that change only to the gate where the change has happened, and then if there are events following that, I will just follow the events. Okay, so I'm going to make my first change, and that is going to make my D from 0 to 1. I'm keeping my C at 0. I'm keeping my Q, well, I don't know what Q is, okay? What it means is this stays 0, this becomes 1. Let's propagate. There is a 1 on the lower input, there is a 1 on the upper input, so this becomes 0. This becoming 0 goes into, just follow the events, right? Follow the events. So this 0 goes into the upper gate. The upper gate sees a 0, the output is no longer a 0, becomes a 1. Now it became a 1, follow the event, now it's the gate right below that. There is a 1 there, there is a 0 there, doesn't change, it's 1. Okay, and there was a 0 here, this is a 1. Notice that no change happened on the cross-coupled structure of the output, and therefore my output remains 0 and my output complemented remains 1. Okay, what it means is nothing, no change. Then I'm going to change my C to 1. Okay, D remains at 1, and let's see what happens to Q. So C becomes 1, this remains 1. Now C has had an event, so let's see what the event follows. Actually, there is this, and that changes the gate right in front of it, and therefore the 1 there, there is a 1 up there, there is a 0 up there, this doesn't change, that remains 1. Then there is this 1 going into the gate, the second gate from the top, okay, and which is this one, okay, and then there's another 1 there, and that changes the output of this gate to 0. Since this output changed to 0, that affects it affects 2 gates. The very first gate, so there is a 0 there, and therefore there is a 1 here, and it also affects the gate below it, and then there is a 0 here, the output remains 1. Also, it affects the cross-coupled NAND in front of it. So there is a 0 here, therefore this becomes a 1. On the lower gate, lower output gate, there is a 1 there, there is a 1 there, this becomes 0. What it means is when the clock changed from 0 to 1, the Q output became 1. Okay. I'm going to make another change. This time I will change my, I will keep my clock at 1. And I will change my D from 1 to 0. Okay. I will change my clock from 1 to 0. And so what is happened, I'm sorry, my D from 1 to 0. So this is what I'm doing now. Okay. changing D from 1 to 0 affects this lowest gate, changes the output. Let's see, the I did not write down the okay, the previous values I didn't write them down, so there is a 1, actually it didn't change, so that's a 0 there, and a 0 here is a 1 here. Okay, this is my fourth value, and therefore I want to make sure that all the nodes have the 3 values already. So the fourth value comes in, and D is 0. D is 0 changes this gate. The upper gate of it is a 1 and a 0, so this becomes a 1. And this input, this is the only place it goes, so the 1 on this gate goes into the upper gate. So I have a 1, I have a 0, and this remains a 1. Okay, and okay, that remains a 1. Then I have a 1 here, I have a 1 here, this remains a 0. And I have a 0 here on the third gate from the top, and therefore this remains at 1. Now let's look at the output. Well, the output structure hasn't seen a change, and therefore this remains 1, this remains 0. And therefore, by this change, nothing really happens. You're beginning to see what is happening, but let me change a few more values, and then you see exactly what happens. What I'm going to do next is my clock goes to 0. This remains 0. So my clock goes to 0. This remains 0. Now let's propagate the blue values. The blue value propagates to the second gate from the top, and what happens is this becomes 1. Also, the blue value of the clock propagates to the gate it's directly connected, which is this third gate from the top, and so I have a 0, but that doesn't change. Okay, now the blue value on top, there is a 1, and on top there is a 1 there. There is a 1 here, so this is going to be 0. And there is a 0 here on the input of the lowest gate, and therefore this is going to be 1. When you are analyzing a NAND gate, as soon as you find a 0 on one of the inputs, you have decided what the output is. Remember, I talked about the controlling values for the gates. Controlling value for AND and NAND is 0. Controlling value for OR and NOR is 1. So as soon as you see a 0 on a NAND gate, then you say, well, the output is 1. You don't have to look at any of the other outputs. All right, so what do I have here? I have 1, 1 on the inputs of the cross-coupled NAND structure of the output. And let's analyze the top gate. There is a 1 there, and then there is a 0, which is the lower gate, and therefore the output remains 1. A 1 on the lower gate and a 1 on the lower gate, the output is 0. So what it means is the output really did not change. Okay? What am I seeing here? Okay, if I had applied this signaling to my to my master slave flip-flop, this one over here, if I had applied that to it, you would see that since D has changed in the middle of the clock, the D value, because I have a transparent gate, when D is 1, when C is 1, I have a transparent gate. Let's look at this here. Okay, see here, look at the left gate. When C is 1, the left gate is transparent, and therefore the changes on D propagates to M. Okay, and at the time of clock changing from 1 to 0, what happens is M is taken and goes on the output. Okay, but we are very clearly seeing that this is not happening here. Okay, this is not happening here. What is happening is the D became 1, and then clock goes from 0 to 1. When the clock goes from 0 to 1, the value of D goes into the output. The value of D goes into the output right there when the clock goes from 0 to 1. Okay? Actually, and then what happens is the clock being 1 doesn't make any difference, doesn't cause any changes. Even if D goes 0, 1, 0, 1, the output is 1 already. So what I'm seeing is this. What I'm seeing, which is very important here, is that instead of having a complete pulse on the clock to take the input halfway in the middle and then all the way to the output, only an edge, a single edge, 0 to 1, causes the value of 1 from the D input to propagate to the output. Okay? I call this an edge trigger D flip-flop. Okay? And here is the Verilog. Let's again say reg Q always. Just write down exactly what you are seeing here. Always on the pause edge of C, that means when you see on the positive edge of C, Q gets D. Okay? Alright, so this is my flip-flop. But then, other questions on this?
So this is the kind of flip-flop that we use in lab, right?
That is the flip-flop that you are using in lab, yes. Actually, that's the most common flip-flop. Okay? And it's called edge trigger. But then I'm also going to let me also go back here and talk about the very long description of this. If you don't look at this blue delay here, and if you assume that inside the duration, within the duration of the clock, D does not change, okay? And if you assume that the timing, the delays are followed, it means that the delays are not violated while propagation is being done, no input changes. If you look at this flip-flop as a black box, what do you see? If you look at it as a black box, you see that when C goes to 0, the value of D goes onto the output Q. Okay? Even though this is not the same structure as this one, but then we can interpret it as an edge trigger flip-flop, and therefore we can also write the description of it as always at, here is neg edge. Of clock Q gets D. Okay? And this is not, like I said, is not exactly neg edge because it really requires that level. It's not happening on the edge. It does require the level. But see, that level, the difference between that level and the edge is what? A few nanoseconds. So if you kind of ignore those few nanoseconds, okay, sometimes it's not even nanosecond. If you ignore that little delay, then you might look at this, okay, this is changing on the edge. If it's changing on the edge, then this will be the description, and this will be the notation for it. This is negative edge, C1, 1D, Q for this, okay? And I use a triangle for the edge. And therefore, going to this one, the symbol for this is C1, D, Q. And then again, I'm showing that my D input depends on the clock input, but then with the clock, I'm showing that triangle, meaning the rising edge. If I put a bubble next to the triangle, then it's a falling edge. Okay? All right, so we have done pretty good, and we have done pretty good with the flip-flops. Remember when we started the latch, we said, let's assume Q is 0. When we started here, we said, let's assume Q is 0. Okay? What if I'm dealing with a real flip-flop? Okay? And the circuit is powered up. What's the output gonna be? Well, it can be 0, it can be 1. What if I want to force it into a certain value? I'm gonna do this. I'm gonna add the signals to this flip-flop to force it into going into a certain state. Okay? All right. I want to add a signal to force my output to go to 0. Okay? To force my output to go to 0, because these are NAND gates here, I bring in a signal like this. And if I put a 0 into, as long as I put a 1 on this black line, nothing happens. Okay? As long as it's 1, nothing happens. As soon as it becomes 0, this output becomes 1. This output becoming 1, this output becoming 1, then the upper gate has 2 1s, and this becomes 0. Okay, so I just added the signal, but there is a problem with it. Well, I just added the signal to the circuit that forces my output to reset to 0. Okay, but then that happens when it is 0. So I call this one active low reset. Okay? It is an active low reset. But then the problem with this is it's really not permanent. Okay? See the 0 and 1, the black 0 and 1 that I have, if I change my R, now it is 0, back to 1, then the black 0 and 1 will go back to what they were before. So this is not a really good permanent resetting. And the reason it is not permanent is because it's not changing the stages before that. Okay? It's just going right to the output and changing the output of the gates. It's not changing the memory. It's not changing the state of the circuit. It's just changing the output. That's why it's not permanent. Okay? If I want to make it permanent so that when it becomes 0 or when it becomes active, the output resets. And when it goes back to 1, which is normal mode, the output remains at that reset value. This is what I interpret as reset. If I want to do that, I have to also affect the stages before that. Okay? That's why I'm going to take this input, not only go to that output, I'm also putting it into this and into this. Okay? Now see how the black line affects. As long as this black line, which is my reset, I'm not going to use a bar. I use a slash, meaning active low. Okay? As long as this is a 1, because these are all NAND gates, a 1 on the inputs of all these NAND gates does absolutely nothing, right? A 1 on the inputs of the NAND gates does absolutely nothing. So the outputs are as they are. But when it becomes 0, let's follow the black line, and whenever it changes something, let's see what it becomes. R is 0, and the first or the second gate from the top, the output of it, because it's 0, becomes 1. The fourth gate from the top, because this is 0, this becomes 1. Okay? All right. There's a 1 there, there is a 1 there, this becomes 0, and okay, so this becomes 0, and now this is 0, therefore this becomes a 1, which we want it to become, and then a 1 there, we get a 1. Okay? I'm sorry, a 0. I'm claiming that these values, at least the output values, are stable. Okay? So what I'm going to do now is I'm going to change my reset back to 1. I'm going to change my reset back to 1. Okay. Now, this changed back to 1, and therefore I have a 1. I have a D of 0. This remains a 1. I have a 1 on the top gate, and I have another 1. So this is 0. I have a 0 here. This is a 1. I have a 1 here. My clock is still 0, so this is a 1. Okay, and then this 1 here, I have a 1, I have a 0, this remains a 1. I have a 1 here and a 1 there, this becomes 0. Okay? So what happened is my R input changed to 0, my circuit resets to 0, and then when it changes to 1, it remains a 1. It remains a 0. That means this is a reset input. The thing about this reset input is that it doesn't require the clock. It means that if my reset becomes 0, I don't need the clock to set the output. Okay? If I want to show the symbol of this, becomes something like this. This was my flip-flop before I add the black line. See? 1, 1, D, Q, and the black line is this. Active low, reset. And notice that this is the reset, this is the clock, this is the D input. Notice that I did not use the number 1 on the left hand side of my reset. Okay? Number 1 on the left hand side of the reset would mean that it's controlled by the clock. This is not controlled by the clock. Okay? It is called an asynchronous reset. And then I'm going to show the very long description for it in a few minutes. And but before that, some flip-flops also require a set input, and then I can do the same thing for similar thing for the set input. For setting it, I bring in my active low set to this gate, and active low set also to this gate. I'm not going to go through the changing and proving it, but just take my word for it that this is an active low set, and this is how it's how the notation looks. Okay, so this is reset, this is set. So this is called rising edge D flip-flop with active low asynchronous reset and active low asynchronous set. Okay, so whether you show this symbol or you just write this text input means the same thing, or this diagram. Now let's go back and write the very long description of it. Okay, again my Q has to be reg, whether it's an output or not. If it is an output, you just say output reg Q, and then you say always. You still have pause edge of clock. Okay, and then you say if There's no if for now. Then you say pause edge of clock, like we have done before, Q gets D. But then I'm saying that in addition, neg edge of reset, and then if tilde reset, okay, Q gets 1 tick B 0. Then we're gonna do this neg edge set, else if active low offset, Q gets 1 tick B1, and then you put this statement that I erased, which is Q gets D. I don't need an end, but if you do like a begin end, this is how it works. So whether you do this, you do this, or you do this, okay, or actually this whole diagram here, they're all the same. All right, there isn't really much more to do with the flip-flops, except that I can always go from one flip-flop type to another. Okay, for example, a D flip-flop, a rising edge D flip-flop, now with or without reset or whatever. If I want to change it to a T flip-flop, this is how it works. If T is 0, then this just circulates the data back into itself, means nothing changes. If T is 1, then it it complements it and puts it back into itself, and therefore this is a T flip-flop. Okay? A T flip-flop is a 1-bit counter. Okay? See, 1-bit counter. 0 becomes 1, 1 becomes 0. And I'm going to show you a few designs. Let me check the topics that we have to cover. Thing before we continue, I have to explain that, and actually it's nothing that we haven't seen before, but then I want to show the difference between the synchronous and asynchronous timings. See, this is my flip-flop C1 1D Q. This is my active low reset. this is my active low set. Okay. What I want to do is put some changes in the input on the input and the clock, and to see how things change. My clock goes like this. Okay, maybe a periodic up and down signal. The circuit is rising edge, and therefore all the changes on D will propagate to the output only on the rising edge. So this is my D. Okay, let's say my D is 0. Then becomes a 1, stays a 1, comes a 0, then becomes 1. Okay, I have a reset input R, which normally I keep it 1. Okay, I keep it 1, but then somewhere down here I change it to 0. Okay, and then back to 1. I have another input set, which is normally 1. Somewhere down here, I set it to 1. And back, set it to 0, back to 1, and then do this. What I want to know is what's my output. Something you are sure about is anytime your reset is active, the output is definitely 0. Anytime your set is active, your output is definitely 1. Okay, it has nothing to do with the clock. Oh, by the way, I didn't say anything about that, and that is, I'm sorry, I didn't say something about this, and that is if set and reset are both active simultaneously, the bad thing that happened to that SR latch is going to happen here. So if you make your S and R simultaneously active, means both of them 0 at the same time, then your flip-flop is going to lose its memory, so don't do that. And I'm not doing this here either. All right, let's say that let's not talk about the rest of the times. Let's say that I start my queue with 0. Okay, outside of the times that set and reset are active, everything else on queue will happen on the rising edge of the clock. So during this rising edge, I'm ignoring the value of during this rising edge, I'm ignoring the value of D, because during this rising edge, reset overwrites everything. During this rising edge, set overwrites everything. Okay? During this, both S and R are not active, and therefore the D input will be taken. So here I have a 0, here I have a 1, here doesn't really matter what I have, here doesn't matter what I have, this is a 0, this is a 0, this is a 1. stays 0. Here it becomes 1. Stays 1 only until my reset becomes active, and then no questions asked, no clock looked for. My output becomes 0. After the resetting, the output remains at 0 until all of a sudden what happens is set comes in. Set comes in, again, no question asked, the output becomes 1. The output becomes 1, stays 1 even after the reset, okay, until an edge of the clock is seen. The output becomes 0, and then the output becomes 1 right here. Okay, so this is what my output gonna look like. And again, this timing diagram is consistent with the flip-flop notation I'm seeing, and also with the always statement that I'm seeing. Look, the always statement says what? It says, if the positive edge of the clock arrives, then only put D into Q if reset is not active and set is not active. Okay? Because those if statements come before putting D into Q. And then it says that if you see R becomes active, then don't even look at the clock. Just if R is active, R is 0, then put a 0 into Q. What this does not tell you is that if set and reset become active simultaneously, the flip-flop loses its value. Okay? In this case, if they become active simultaneously, it resets it. Okay? I could make that consistent too. I could say that if tilde R and tilde S, that means both of them are active simultaneously, then put some X into Q or something like that, indicating that it has lost the memory, its value. Alright, so this is the timing diagram for this flip-flop. Now let's go back to what I started saying here. A T flip-flop is a 1-bit counter. So, this is what I'm going to do. For now, let's not worry about the structure or how it's built. Let's only be concerned with making something useful out of it. So I have a T flip-flop, and if the T input is 1, each time my clock goes from 0 to 1, okay, each time my clock goes from 0 to 1, this toggles, and therefore this can be regarded as bit 0 of a counter. Okay, then I put another bit here, another one here, another one here. Okay. I want to build a 4-bit counter, a 4-bit up counter. Okay. I've already built one of the bits. Not much achievement, but looks good. Q3, Q2, Q1, Q0, Q3 plus, Q2 plus, Q1 plus, Q0 plus. Actually, this is the first design I want to do with this flip-flops. 0, 0, 0, 0. Okay, I'm going to write all of these. Zero, 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 zero counts up to 0, 0, 0, 1. 0, 1 counts up to 2. 2 counts up to 3. 3 to 4. 4 to 5. 5 to 6. 6 to 7. 7 to 8. 8 next count is 9. 9 next count is 10. 1 0 1 0. 10 next count is 11. 11 next count is 12. 12 next count is 13. 13 next count is 14. 14 next count is 15, and 15 rolls over back to 0. Okay? Look. The first bit is good, is easy. Because you look at the list on the left and the list on the right. For every count, Q0 to Q0 plus toggles. See? 0 becomes 1. 1 becomes 0. So it's easy. It just toggles. Okay? That's why when I put the clock in there, this will do the job for my Q0. Now let's look at Q1. Q1 does it toggle every time? See, Q1 toggles here, but then doesn't toggle until here, doesn't toggle until here, every other time. If you look at it carefully, you find that the second flip-flop, what can you tell me about this? The second flip-flop, what happens to it? It only toggles when the right flip-flop is 1. It only toggles when the right flip-flop is 1, or the flip-flop to its right is 1. Okay? So, what I'm going to do is take this output, bring it into the T input of the next one. Now let's look at the next one. The next one, or flip-flop number 2, it also toggles, but less frequently. Okay? It toggles here. It toggles here. It toggles here. And it toggles here. What's your observation now? Say that again. When both flip-flops to its right are both 1. Okay? So this is how I'm going to build the input of that. When just 1 second, let me this is 1, this is 1, this toggles. Okay. Now let's look at the leftmost flip-flop, and there still toggles, but then it toggles okay, it toggles here and here. What it means is that it toggles only when all 3 bits to its right are 1. Okay, so how do I build this? Well, I already have a gate output which ends the bits 0 and 1, and then I'm gonna put a gate here to take this and to take this. Okay, and then bring this into the T input. For the next bit, if I want to build that, I also take this and send it out to the output, to the left hand side. Okay. So one way of doing these flip-flops is this. I can say that I'm going to build this flip-flop with C, T, an AND gate, and it has 2 inputs coming into it, 2 outputs going to the left. Okay, so whether I need the AND gate or not, I can just repeat this. Not means what? Means for the rightmost flip-flops, I don't really need these AND gates. Okay, but that doesn't really matter, because what I can do is for the rightmost flip-flop, if I do have that AND gate, then if I tie the 2 inputs together, if I tie these 2 inputs together and put a 0, then what happens? The 0 on the rightmost flip-flop, this is bit number 0, Q0. Okay. The 0 on the rightmost flip-flop, on the AND gate of the rightmost flip-flop, propagates all the way 0 to all the AND gates. What it means is, whatever you clock it, it's not going to change. Okay? And therefore, I am using this as an enable for my for my counter. Okay, that's one thing. The other thing I have is the very rightmost flip-flop has an output and an AND gate. An AND gate. Okay? And if I take the final output, now this is the Q0. If I take the Q3, which already has a 1T input, it already has a, notice that it already has the AND gate, it already has two inputs coming into the AND gate, it already has the output going out, so that maybe bit number, this is Q3, bit number 4 wants to use it, okay? But if there is no bit number 4, what I can do is put another AND gate here. And this AND gate output becomes 1 when the rightmost bit is 1 and the flip-flops, all of them are 1. Okay? I'm calling this one carry out. The two inputs of the Q0, I'm calling one of them carry in and one of them enable. Doesn't make any difference which one you call what. Okay? So the way it works is if enable is 0, you are not counting. If carry in is 0, you are not counting either. Okay? If carry in is 1 and your count reaches 1, 1, 1, 1, okay, your carry out is also 1. Okay? And this is good. This is used for cascading all of these together. Okay? So let me show you the structure I'm talking about. This is a 4-bit counter built out of those little structures. It has a clock input. It has this AND gate things. And then it has a final AND gate as well. Carry out. And then the way the clock works is the main clock goes into all of these bits. Okay, this is a 4-bit counter, up counter. And this I regarded as carry in, this I regarded as enable. If you decide that you want to take 2 of these and build an 8-bit counter, okay, it has a carry in, it has an enable, it has a carry out. Okay, connect the carry out of this to the carry in. Put a 1 on the carry in of the right one. Connect the 2 clocks. And then connect the 2 enables. And then this is your Q0, Q1, Q2, Q3, Q4, Q5, Q6, and Q7. Okay? That's a 4-bit counter with made with cascadable little counter elements. Okay. I'm going to do another counter for you, a little bit cheaper than this, and then I also show you the problem with it. Okay, so I'm going to go back to another counter here. And I'm going to do the table again. Okay. Q3, 2, 1, 0, Q3 plus, Q2 plus, Q1 plus, Q0 plus. This is a T flip-flop again. And I'm gonna make this is my clock input. What it means is when the clock goes from, unlike the previous one, when the clock goes from 1 to 0, this toggles, and I'm claiming this is the Q0 output, which it is. Okay? Not very different from the structure I have here. So anytime clock goes from 1 to 0, this one toggles, and therefore this is indeed a bit number 0 of my counter. Okay, and here I'm seeing this. This is toggling, this is toggling, this is toggling. Now bit number 1, the next bit, the next bit, and the next bit. The reason I'm using this inverter is because I do want falling edge flip-flop, okay? But then I will either have an inverter put in there, or I just go grab a flip-flop with falling edge clock, okay? And if I put the inverter symbol, it means that I have a rising edge, I'm turning it into a falling edge. But then if I use this symbol, it means that it is indeed a falling edge flip-flop. Okay, so do whichever you want, but in any case, I want the end effect to be that this is falling. All right, let's look at Q1 now. Q1 toggles here, or it toggles here, or it toggles here. If you look at that, you find that actually my flip-flop 1 is toggling anytime that my Q0 is going from 1 to 0. Okay, see here, it's toggling, right? Look at the orange blocks. It is toggling when the Q0 is going from 1 to 0. So this is what I'm going to do. I'm going to take the output of Q0, put it into the clock of this one. And this becomes my Q1. Now I'm going to look at, I'm just going to use the same color. Now I'm going to look at the third one, and then I'm seeing that Then I'm seeing that the third flip-flop toggles 0 to 1 here, 1 to 0 here, 0 to 1 here, okay, and then finally 1 to 0 here. The third flip-flop toggles when the flip-flop to its right changes from 1 to 0, and therefore I'm going to take this, bring it here, put it here, and this becomes my Q2. Same thing with this, and this is my flip-flop 2. And then you see that with the last flip-flop, the same thing. The last flip-flop toggles, changes from 0 to 1, changes from 1 to 0. I only have one requirement, and that is the bit to its right changes from 1 to 0. And therefore, this becomes my Q3. Okay? This is good and it works. But let me show you one situation here where you have a clock okay, let's say Q3, Q0, Q1, Q2, Q3 is 1, 1, 1, 0. Okay. So it was 6, now it's 7. And the rightmost flip-flop because the input changed from 1 to 0, see, the clock input of it changed from 1 to 0. After a delay, it changes from 0 to 1. Okay. So it's okay. And then my other outputs, a 1, a 1, a 1. Let's say nothing happens until the next clock. The next clock changes my Q0 from 1 to 0. Now, the 1 to 0 on Q0, that causes Q1 to toggle, and therefore Q1 doesn't really toggle until Q0 completely changes to 0. So this. Next one doesn't change until Q1 completely changes to 0. What it means is this. See the delays I'm drawing here. The next one has to wait for Q2 to change, and therefore that doesn't change until Q2 changes to 0. And what's the problem here? What's the problem here? The problem is the falling edge of the clock arrives, and then not all outputs necessarily change at the same time. Because the outputs depend on each other, one has to change, and then the other ones have to change, and so on. Okay? Not only it has a long delay before it settles, but also there are some incremental times that your output is showing something wrong. Okay? Look at somewhere between those delays, it's showing 1110, and then it's showing 1100, then it's showing 1000, and then it's showing 0000. Okay? Not all outputs are changing at the same time. Whereas this counter is a much better counter, and even though there is delay there because we have to wait for the AND gate output to become stable, but once the clock arrives, they are all clocked at the same time. They're all clocked at the same time, and therefore this the outputs change at the same time. This is called a synchronous counter. I have a hard time saying asynchronous or asynchronous. This is called the synchronous counter. Whereas this one, because the outputs don't change at the same time, this is called an asynchronous counter. Okay? But then the good thing about this one is cheap. You don't even need those AND gates. And then also this input of it, I'm sorry, this is not D, these are T. This one acts like the enable, and if this is 1, it counts. If it is 0, it doesn't count at all. Okay? All right. So we did the flip-flop, and then we came up with two designs, two counters, and let me see if there is anything to be said. Okay, about this design, where I'm taking the output from one flip-flop, bringing it into the clock of the next one. Like I said, even though it's cheap, it's not a good design. It is asynchronous. Okay? For now, whatever we do, we take the clock very seriously. So let's talk about the clock. Okay? I never gate the clock. I never take an output of a flip-flop into the clock. I take one single signal for all circuit clock inputs. Okay? I don't play with the clock. I don't gate the clock. I respect the clock. If I respect the clock respects me. If I don't respect the clock, the various parts of the circuit start clocking at different times, and then a lot of bad things can happen. Okay? In a small design, in something you are doing in lab just to test something, maybe you like to do that. But in big designs, you cannot do that. Okay? You have a part of your circuit. Let's say this is a big circuit on an FPGA, maybe on something. This part of the circuit has a clock coming into it. This part of it has a clock coming into it. There may be a big distance between these. And this distance between these two parts of the clock is causing a delay from this clock to this clock. This is called clock skewing. Okay? Meaning that the left circuit and the right circuit, the left circuit maybe is being clocked here, but then the right circuit being clocked here. Okay, because of the delay between the because of the delay in this line over here, and we don't like that. And that's why in big circuits what you have is a clock distribution logic. Okay, this is where I said you respect the clock. You create a clock distribution in a form where the clock is, some logic is put on the clock so that it arrives in all parts of the circuit approximately the same. What it means is that you start with a single clock, and wherever it goes, you put enough inverters on it that the count of the inverters wherever it goes is the same. And that logic is called clock distribution logic. So the key is respect the clock. When we are doing a clock circuit, we don't play with the clock, we don't participate the clock even in the designs. Okay? We don't participate the clock in the design either. What it means is that when I want to do a counter like this one, for example, okay, I bring the clock, connect it to all my flip-flops, and say, now, let's start from now. Okay, let's start from this point on. Or in the designs that we'll be seeing tomorrow, I'll show you that I do all the designs, I do all the logic, I do all the flip-flops. At the very, very end, I say, okay, what kind of flip-flops am I using? Okay, maybe I'm using a flip-flop with set and reset and a clock. And then at the very end, I tie the set, reset, and the clock to the external circuits, set, reset, and the clock, and none of those have ever participated in the logic of my design procedure. Okay? Alright, this is fine, and we will be continuing the same topic of the counters and then going into state machines next time.